Space, the final frontier. Or is it? It's been 50 years since we first landed on the Moon. Since then, our probes have explored the deep reaches of our solar system. The International Space Station has been continuously inhabited for nearly 20 years. These are impressive accomplishments, but when will we be able to actually live on another planet? To examine this properly, we should probably address some important cosmic questions, such as what actually is a planet? How do they differ? And which will be the most viable as a home? And while we're at it, what happened with Pluto? Well, our solar system is based around a star, the Sun, and everything that orbits around it because of the Sun's gravitational field. It's been kicking around for the past 4.5 billion years after the collapse of a giant interstellar molecular cloud, but that's actually not important right now. Our solar system consists of 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And since 2006, a planet has been defined by 3 key criteria. Firstly, it must be a celestial body that orbits a star, the Sun in this instance. Secondly, it must assume a hydrostatic equilibrium, or rather it has to have rounded itself for a balance of its own outward pressure and its own gravitational force inward that stops it dissipating out into space. A good starting point for a stable home, I think you'll agree. And thirdly, it must have used its gravitational force to clear its surrounding area of significant debris, such as stray rocks. Now, that might sound like a bit of a mouthful, but that last point is important because it's why Pluto is no longer considered a full planet and instead a dwarf planet. Because while Pluto is spheroidal, more or less a sphere, and orbits the Sun, it hasn't had enough gravitational force to clear its local area of debris, such as rocks. So, sorry, Pluto. We're all aware that our solar system is pretty big, but the true scale of the planets and the vast distances between them are often tricky to demonstrate or even imagine. Thankfully, with some creative thought, a little ingenuity, and an empty space center, we can provide a little more perspective on this.
When most people think of the solar system, they tend to think of a model a little bit like this one. So the Sun in the middle, your 8 planets in a line, and the size is pretty much the same. In this order, we have Mercury, Venus, Earth, Mars. Those are your rocky planets. You then have the king of the planets, Jupiter, Saturn, Uranus, and finally Neptune. So this is a great model for helping us to remember what's in the solar system, but it is pretty unrealistic in terms of the actual sizes of the planets and how far away they are from each other. So I suggest we build our very own solar system to scale. So first step, we'll get rid of this. To build a scaled solar system, we first need a sun. So I have this yoga ball here. It's about 70 centimeters across, and this is going to be our sun. And on this scale, this is about 2 billion times smaller than the real solar system. Our first planet, Mercury, will be no bigger than a sesame seed on the tip of my finger. So I'll put that here. To scale, 2 billion times smaller, Venus, our next planet, is the size of a small dried pea. Moving on, Earth. Earth is slightly larger than Venus, not much, the size of a slightly bigger pea. Moving on to Mars. Mars is actually pretty small, so it's about half the diameter of the Earth, and it's the size of a peppercorn on our scale. Now we move on to the gas giants. The king of the giants, Jupiter, is about the size of a tennis ball on this scale. And as you can see, you can fit a lot of Earth inside Jupiter, about 1,500 of them. Saturn, our glorious ringed planet, is about the size of a lime on this scale. And then finally we get to the icy giants. And these icy giants are about the size of large marbles. So there we have it. This is an accurate, to-scale model of our solar system, shrunk by a factor of 2 billion. Now, of course, this is great for seeing the size, but this doesn't tell us how far away the planets actually are from each other. So what we're going to do is build a model of just how far away on this scale the planets really are.
So now that's cleared up, let's look at each of the 8 planets in turn and assess how suitable they'll be for human habitation. Conveniently, they can be broken down into 3 broad categories. Starting furthest from the Sun, we have the ice giants, Uranus and Neptune. Yes, ice giants. It's not really looking promising if you're dreaming of a warm new home. While initially categorized as being gas giants, it was later discovered that their construction was quite different. They're mostly comprised of elements heavier than hydrogen and helium, like oxygen, carbon, and nitrogen. And these chemical compounds were solid at the planet's formation, either as frozen water or within ices. That's a term we use in astrophysics to describe volatile chemical compounds with freezing points above 100 Kelvin. That's minus 173 degrees Celsius, such as water and methane. However, due to the extremely high pressures and extremely low temperatures found in these planets, they exist as supercritical fluids, meaning that they have a blur of gas and liquid properties. Supercritical, volatile, icy, hardly words that you'd look for in an estate agent's property listing. Moving onwards and inwards, we have the gas giants, Jupiter and Saturn. These planets are predominantly made of hydrogen and helium, though again, because of the extremely high pressures that exist here, they exist at their critical point, where they have limited distinction between liquid and gas. This again doesn't look promising for easy living, not to mention trying to navigate those ice rings that encircle Saturn on your way over. Finally, we have the terrestrial planets. Orbiting within the asteroid belt, these inner planets are composed of rock and metal, and are the ones closest to the Sun: Mercury, Venus, Earth, and Mars. What makes these planets significant, not least for us wannabe relocators, is that aside from a metallic core and a mantle, they have a solid surface, which of course is vital for everyday activities like landing spacecraft, walking around, building single-story rear extensions. And these rocks can also form exciting scenery, mountains, valleys, scenic vistas that we can enjoy in our new homes. We should also give a shout out to moons. We visited our moon and found the surface to be solid, but there to be almost no atmosphere whatsoever. So if we wanted to live there, we'd have to bring our own life support. The moon does improve life on Earth. It gives us oceanic tides, for example, but in terms of living there full time, it's pretty much a no-go. Jupiter's moons have some habitation potential, but they are a wee bit far away. So for the time being, let's focus a little closer to home on our neighbours. A key issue to address before we start thinking about setting up home on another planet is how we get there. Many of us are used to the strains of long-haul flights, but reaching another planet is a whole other kettle of fish. Our closest neighbour, Venus, can be a mere 43 million kilometres away, but Neptune, at its furthest from Earth, is 4.3 billion kilometres away. Great for racking up air miles, not so good for popping home on the weekend. But what do those numbers really mean? How long would it take to reach those planets? Well, there are no commuter services currently running, but we can have a guess at how long it would take by how long it took for probes to reach those planets. The Cassini probe took 7 years to reach Saturn, courtesy of a gravitational assist from Jupiter, while the Curiosity rover took 7 months to reach Mars. However you cut it, it's a long time to spend cooped up in a spacecraft. To find out more, let's talk to Tamala. Historically, what have long-term space missions been like?
Well, historically, we actually had much shorter missions. So the very first missions to space just went up and came down again quickly, or even to the moon. It was 3 days there, 3 days back. So you're talking about a week total for the astronauts, and the type of person that you're going to select to go and do that is completely different. That's going to be a pilot, someone that's very used to coping with short duration, high intensity missions. Now, we send people to the International Space Station for 6 months at a time, or sometimes even a year. And the type of person you need for that is completely different. You need someone that's a really good team player, someone that doesn't get bored easily, ideally maybe a scientist that can do some work along the way, or an engineer that can plan out the base that you're going to live on in the future, and very much someone that is going to get along with lots of different personalities, because for 6 months or a year at a time, that's all you're going to see. You might see 6 other people on your mission.
So what problems have astronauts faced then in long-term space missions?
Space is not a natural environment for humans to be in, so we have to keep them protected inside the space station. Radiation is an issue. Low Earth, we're protected by the magnetic field and we don't get the radiation from the sun as much. The longer we spend in space and the further away from Earth we are, the more exposed we are to the radiation. So we could be looking at radiation sickness as a potential hazard for astronauts. So it's one thing that we're really concerned about. The body is very good at getting rid of what it doesn't need. So if you're floating in space for 6 months at a time, you lose 10% of your bone density and you lose about 20% of your muscles. And that's just because your body knows that it doesn't need it. They're floating around in space, you're not working against things, and it just gets rid of what it doesn't need. It's very efficient that way. So we actually have to get the astronauts to exercise 2 hours a day just to maintain muscles as much as possible, try to simulate impact so the bones keep their density and keep them as healthy as possible through the diet as well. So work on the International Space Station helps us to then think about what we're going to need on the Moon and Mars in the future.
What challenges would astronauts face then on a long-term mission?
The effect on astronauts of being in a very sterile environment, kind of like the environment around me, is something that we definitely test on the International Space Station. So it's noisy, it's mechanical, there's vents constantly circulating air. It's not what we're used to. When we select astronauts now, they very much go through a psychological screening as well as a physical screening. So they have to prove that they are calm under pressure, that they are excellent communicators, they have good leadership skills as well. And all of this is built into the testing process.
So who would you pick to go on a long-term space mission?
The ideal person for a space mission is someone that is an amazing team player. So you know this person because they get along with everyone. They're always happy to go the extra mile just to make sure that everyone's kind of happy and working together. So not a big ego. Someone that's a bit of a jack of all trades as well, so very good at maybe tinkering with things or fixing the kitchen sink if it goes wrong, but also happy to dive into some research, knows a bit about astronomy or navigation, that sort of thing. A very good communicator as well. So the astronauts that we send to the Moon or Mars, they are our voices, they are the representatives that we're sending out, and they need to be able to capture that and bring it back to us and kind of share with the rest of the world. So someone that is able to capture what they're seeing in a language that we can all understand.
So assuming that you survive your long, arduous journey, exhausting your supplies of downloaded music, TV, perhaps mastering solitaire, you next have to worry about how to sustain life on your new, far-flung home. Based on our overview then, the terrestrial planets look like our best bet. But we can actually hone down our list a little bit further. Mercury has basically no atmosphere, whilst Venus has too much atmosphere. The surface pressure is immense. So, crossing those 2 planets off of our list, we are left with Mars as being our best bet. So, let's take a closer look at some of the practicalities of what we need to make life on Mars happen. First of all, what's Mars actually like to be on?
Mars as a planet is incredibly hostile. It's very, very arid, a bit like a desert, very cold, much colder than people realize. Average temperatures around -50 degrees Celsius. So you need materials if you're going to land there that can withstand extreme ranges of hot and cold and be able to operate in every condition. It's also extreme geology. We have some of the highest mountains in the solar system, the deepest canyons, so very much a hostile place that we would really have to adapt to if we're going to live there. Mars also has a very thin atmosphere. It's 100 times less pressure than here on Earth, so any habitat or walking around, you're going to need a suit on to keep the pressure. You're looking at 1/3 gravity, which means our astronauts on Mars are going to be kind of loping along. It also lacks a magnetic field. Now, we take this for granted here on Earth, but the magnetic field on Earth shields us from radiation from the sun. And on Mars, radiation is going to be a big problem. The other challenge, as we've learned from the rovers that we send to Mars, is dust. So Mars has these global dust storms, not very powerful in terms of wind, but the dust gets everywhere. And as we've seen with rovers, if the dust lands on the solar panels, that completely gets rid of the power source.
So despite its challenges, Mars seems like the obvious choice. But there are some glaring problems, such as a complete lack of running water and supermarkets. So how do you go about sourcing the food we'll need to survive?
One of the most important things for astronauts' well-being and health is the food that they eat, not only for their own nutrition, but also for the memories of home, the taste of their favorite foods. So this is a selection of the types of food astronauts have eaten throughout the years. To start with, food came in giant toothpaste tubes. They weren't entirely sure astronauts could eat solid food in microgravity, so they tended to mash it and puree it and put it in tubes. They realized that solid food was okay as long as it didn't float around in too many different pieces, so they would start to put things in tins. You want to introduce a lot of protein, a lot of calcium into the diet to replace the bones and the muscles that are lost. Here we have a snack. This is some almonds, so again, introducing a lot of nuts and protein into the diet. And finally, this is probably close to what astronauts eat today. So this is a vacuum-packed southwestern corn chowder. And you might notice we've got the Velcro on the side because things tend to float around, and if you don't stick it down, you will lose your dinner. So food has become more and more appetizing over the years, but of course we can't take everything with us on a long duration mission. So we need to understand how to make things as sustainable as possible, to make a self-enclosed biosphere where everything we produce is reused, recycled in some way. So we're exploring ways that we can do this on a smaller scale. So we're growing plants, we're recycling the wastewater, so the urine they produce is actually purified through a centrifuge and filters and recycled for drinking water. All of these techniques help us to explore space further, but they also have helped us to be more sustainable here on Earth as well.
So there's potential for food and drink, and the appealing prospect of reusing our own waste. But what if you want to go outside and stretch your legs on a walk? Well, you'll need a suit, like one of these, specially designed to protect you from the myriad dangers on the planet. On Mars, that's mostly going to mean two things: the extremely low temperatures, so you'll need a suit with lots of thermal insulation, and also a suit with a protective outer layer to protect you from the extremely low pressures and prevent a risk of depressurization. So, apart from finding new locations to support the human race, how has space exploration helped us to live better here on Earth?
Everyone thinks of the astronauts on the moon, they think of going to Mars when they think of space exploration. But actually the majority of what we do in space is Earth observation. We have satellites in orbits that help us to communicate things, to share the breaking news from around the world, the GPS satellites that help us to navigate. So actually the majority of what we do focuses on the Earth, and it's satellites like the one behind me. This is Meteosat, it's a weather satellite. And this goes straight to the Met Office. It gives us 15-minute updates of what the weather is doing. It helps us to understand the climate and to look at things like deforestation, illegal fishing. Some of our satellites can even start to pick out movements in wildlife. So we can see colonies of penguins from space in Antarctica. We can look at the biodiversity of the entire planet and see how that fluctuates with the seasons. So without this global perspective, we simply wouldn't understand the Earth as well, and we wouldn't be able to take the steps that we need to protect it.
Well, it sounds like we have a lot of this stuff figured out already. So, what's next?
50 years on from going to the moon the first time and proving it's possible, now we've had a few decades of testing humans in low Earth orbit. We're now looking at going back to the moon. So NASA, the European Space Agency, they're looking at a space station on orbit around the moon and then on to Mars. Very collaborative in a way that it wasn't before. You have different players, you have commercial spaceflight companies, so very much an exciting time.
So when will we be able to live on another planet? Well, it's a work in progress, but there is a firm belief in many that some of us could be Martians before too long, and potentially sooner than you might think. There are numerous Mars-focused missions and explorations underway as we speak, so who knows where we'll be in another 50 years. One thing we do know for certain is that our solar system has had a huge impact on our everyday life here on Earth. But as for when will we be spending our summer holidays on the surface of Mars, well, we'll just have to watch this space.